In another video, we talked about the peritectic or incongruent melting of enstatite. Here we're going to talk about the so-called peritectic relationship. There's a very nice diagram from John Winter, which we're going to use from his textbook, figure 6.12 for the edition I'm using. The peritectic is this point I that represents this reaction relationship. So what do we mean by that? Well, in the melting case, we took enstatite, heated it up, and it decomposed into olivine, plus this silica-rich liquid over here. I will try to draw that. There we go. So there's that more silica-rich liquid. Not very silica-rich, but silica-rich relative to enstatite. Well, that represents a reaction, although in the melting, it's kind of the reaction in reverse. When we talk about a reaction, we usually think of it in this respect. Let's say we had a pure enstatite liquid. Let's get that bulk composition right on top of the enstatite point. So we take that liquid and we cool it, and the first thing we create, as you can see, would be the mineral olivine. Olivine would crystallize first, even though we have a liquid that's made of pure enstatite composition material. As we cool that system, the liquid will migrate down that liquidus until it hits that peritectic point I. And when it hits that peritectic point I, that's when we have the reaction relationship where the silica-rich liquid will react with the olivine that's been created to create enstatite. Now, it just so happens that if we have a liquid that is precisely made of enstatite, then we're not going to create a whole lot of forsterite. We're just going to create a little bit of forsterite as we go from this initial saturation temperature here, just below 1600, down to 1557. And there will be just enough liquid plus forsterite that the two will completely react with nothing left over, and all we will have is the enstatite that is the product, forsterite plus silica. If you take 1 mole of this and 1 mole of this, you would get actually 2 moles of this, and there will be just enough to get that to balance. What if we have a composition over here? Let's consider the crystallization case again. We would cool until we hit this temperature here. The first crystals of forsterite, we're hitting the forsterite plus liquid field. So the first crystals of forsterite would form about 1840 degrees centigrade. And as we cool the system, the liquid will migrate downwards towards that reaction point. They'll hit the peritectic, but we've created so much forsterite along that curve that as that liquid reacts with the forsterite, we are going to have some forsterite left over. Actually, we'll have quite a bit left over. As we follow this bulk composition down, we're going to end up in the forsterite plus enstatite field. So we'll have a rock with 2 minerals, olivine and pyroxene, and you can see it's more to the left of the halfway mark. We'll have more forsterite than we will enstatite. So this is a case where we have this reaction relationship where we have forsterite in excess of liquid, and so the liquid will completely disappear as it reacts with forsterite left over. What happens if we're over here? So now we're going to enter this eutectic point over here. The first crystallization point, the first crystals to form will be at this temperature here, just below 1557. We're going to follow that horizontal line across. We're not going to make forsterite anymore. There's no more forsterite. We bypass this peritectic point. The first crystals we make are enstatite, and the liquids will move down this curve. The way I've set it up is we've got a bulk composition over here, maybe a little bit to the left of that. It doesn't really matter. And so the liquids are going to move down this intersection here until we hit the eutectic point, and then this acts just like the eutectic that we saw for diopside plus anorthite, where in this case, we're going to make enstatite plus cristobalite. Let's come back to the main diagram. At 1543, we're going to have liquid. Well, let's take our bulk composition here. Eventually, we're going to end up with a rock that's in the enstatite plus cristobalite field. So at 1543, cristobalite joins enstatite. The 2 minerals crystallize together until all that eutectic liquid is gone. The liquid, by the way, is fixed at this composition here. Enstatite and cristobalite will crystallize out in fixed eutectic proportions, whatever the proportions are there. You'd want to renormalize to set enstatite to 0 and silica to 100 if you want to get the precise proportions. And then the system will be completely solidified, would follow the bulk composition down. And now we just have a rock of enstatite plus cristobalite, and at 1470, the cristobalite transforms to the other silica polymorph that's shown here, tritomite. And so nothing really exciting happens there except for that polymorphic transition. If we take any bulk composition from this point to here, so from 1690, that 1695 intersection out to 1543, it's the same kind of eutectic diagram that we've seen before, except here, now cristobalite will crystallize first. We follow this horizontal line across. We hit the cristobalite tie line. Cristobalite crystallizes, drives the liquid towards enstatite at 1543. We have a eutectic liquid right there, and enstatite and cristobalite will crystallize together until the rock is completely solid. What happens if we are at the right? Let's get rid of some of these curves now. Let's say we are to the right in this two liquid field here in terms of our bulk composition. Let's say we're somewhere between here and there. What's going on? Well, let's just take this guy here. It doesn't really matter. We're going to have a liquid that will cool, and now it's going to break up into two liquids. And the liquid that is going to form, notice we cross this. This is called the consolute point if you want to impress your friends and relatives. If we take the tangent of that curve up at the very top, that horizontal tangent, that's called a consolute point. Anyway, we are going to follow this bulk composition down to wherever it hits this solvus. But this is a solvus not between two minerals that we saw with albite orthoclase, but with two liquids. We're going to create a new liquid that didn't exist before that's going to be way out over here, that's a little more silica rich. Now this is our bulk composition here. As we drop the temperature, we're going to have a liquid that evolves along this part of the solvus, so this liquid would become even more silica rich. But then we have a liquid over here that's going to become more magnesium rich. So the liquids are becoming further and further apart as we sink downwards in temperature. So here's another liquid over here and another liquid over here. Drop the temperature further. Now the liquids are even more extreme, more silica rich and more magnesium rich. So what happens as these liquids approach a temperature or reach a temperature of 1695? Well, for this liquid over here, it's not really all that interesting. It's just a new, you could treat it like a new liquid composition that's just going to follow downwards and hit that enstatite plus cristobalite eutectic. How about this liquid way over here? This liquid was coming down towards this eutectic here that now involves the mineral cristobalite. So for the case of both of these liquids, we have a eutectic here and then an inflection point here. These liquids are now going, well, this liquid here, the eutectic liquid here, is going to disappear. It'll be consumed as we crystallize cristobalite. So now as we go to lower temperatures, instead of two liquids, we now just have one. So at this point here, this liquid that was becoming more silica and silica rich is eventually going to precipitate out cristobalite. The parts of it that are not cristobalite are going to add to this liquid over here. And as we go to lower temperatures still, we've left this bulk composition the same. Now we're just back to our usual case of eutectic, where whatever liquid's left is going to follow this curve until we hit 1543. But because we have this early precipitation of cristobalite, we're going to have more cristobalite in the rock than we did when we had a bulk composition over here as we did at A. So this rock A is very close to enstatite. It looks like it's probably about 80% enstatite. Remember, you have to renormalize those numbers to look at the mineral proportions in the rock. You'd want enstatite to be 0 and quartz to be 100%. So this guy looks like it's going to be about 80% enstatite, where this guy here is close to about a 50-50 mixture of enstatite plus quartz. So if we take any liquid anywhere in between let's say this point here between that eutectic and that inflection point, the same thing happens. We get two liquids, one migrates down to the eutectic, the other migrates down to the inflection, and below 1695, that eutectic liquid disappears as we create cristobalite and add a little bit of mass to this liquid over here that now moves downwards. The last part of the diagram is this fellow over here that we could barely see. Let's see if we can get PowerPoint to allow us to draw a line that is going to fall not at the eutectic and not at the boundary, but somewhere in between. Well, it looks like it's not so easy to do, but it doesn't really matter for our purposes. We have this little eutectic here. If we have something that, let's say, intersects at this small eutectic curve here at just below 1713 degrees temperature, that would be the first temperature at which it would form cristobalite. So that is a cristobalite plus liquid field. So cristobalite plus liquid is here, but it's also in that little cell there. We're going to make cristobalite plus liquid a little bit below 1713. Once we get here, we reach that eutectic. We are going to have cristobalite, and now the liquid that will be left, and it'll just be a vanishingly small amount of liquid, will now be in this composition, and that tiny little bit of liquid will eventually find its way to the enstatite plus cristobalite eutectic. So everything from this, unless you're on pure silica, anything that is not pure silica but has even the tiniest amounts of a magnesium component to it, it'll eventually generate a liquid that'll hit that, oh, we don't need to move the whole diagram, that'll eventually hit that eutectic here. How do we know? Because you can look at where the bulk composition ends up. If we put a bulk composition there, and finally we got PowerPoint to mark something at about 98% silica, look at where that bulk composition is going to end up. That bulk composition is going to end up in the enstatite plus cristobalite field. Just barely. It's not going to make a lot of enstatite. Just a tiny little bit of enstatite will form. But the only way you can make enstatite is having a liquid that migrates along that curve. Because the only other thing that's happening in this diagram, you could plot horizontal lines as tie lines, is you're connecting a liquid with a pure silica phase, in this case being cristobalite. So any bulk composition that is off that pure silica tie line and so long as it's to the right of the peritectic, everything between there and there will eventually end up at the enstatite plus cristobalite eutectic, where you'll make a rock of enstatite plus cristobalite. Actually, any bulk composition, I'm mistaken, it doesn't have to be to the right of the peritectic. Anything between enstatite and quartz will end up at that eutectic. So over here, if we have a composition there, we'll make a little bit of forsterite first, but that forsterite will react out. We'll end up with a liquid that will follow here. So even if you're just barely in between the peritectic and that endpoint. So if you have a bulk composition, let's take this. Let's say you have a bulk composition that's here, you'll still end up reaching this eutectic here, as that is the only place that these bulk compositions will have liquids that will allow us to make cristobalite, as we must, because the bulk composition is going to end up in the enstatite plus cristobalite, and at lower temperatures, the enstatite plus tritomite fields. So that's it for our discussion of the peritectic.